Okay, so welcome to the Tutte Colloquium, and our speaker today is Chloe Martindale from University of Bristol. So Chloe obtained her PhD in 2018 from University of Leiden and University de Bordeaux. She specializes in number theory and cryptography. So today she's going to talk about constructing broken SIDH parameters. So Chloe.
Thank you for the introduction and for the invitation. It's fun to be able to speak in Canada from my office in Bristol, or my home office in Bristol. So yeah, this is basically a talk about me trying really hard to break one of your own home researchers' scheme, and you'll be glad to hear failing again. So this is SIDH. I'm sure you've heard about being in Waterloo, but I'm going to recap it because I know this is a colloquium, so I'm going to try and keep it down to earth and at least go over what it is before I talk about our latest ideas on, since we can't break it, we'll construct things that we can break. So this is really about how serendipitous the choices made by Luca Di Feo, David Zhao, and Jerome Plut were back in 2011 when they invented this cryptographic scheme, in a way that it seems that it's just at that sweet spot where none of our ideas work. So first of all, I'm going to, as I said, I'm going to probably recap for most of you, maybe not for all of you, what this is about and what we're doing here. I should say, feel free to, unmute and ask a question, or I don't know if I can see the chat, but I assume someone will shout at me if there's a question in the chat. So do forgive me if I'm going over things that you already know. I know the Waterloo crowd is probably more clued up about isogeny-based cryptography than anywhere else, really, but I thought it was best to be on the safe side. So first of all, this is some just standard crypto that you will have seen if you ever took a crypto course in your degree, or if you've been to any other talk on public key cryptography in your life, which is the Diffie-Hellman key exchange from 1976. And typically what we're working here is we have, first of all, a setup where we have public parameters. So that would be some finite group G, which in 1976 was the multiplicative group of a finite field FP. And in these days, we also use elliptic curve groups. And, oh, that's not meant to be a P. I should have fixed that. An element G in that group of prime order. And that's not the same P as the P on the line above. That's terrible. I'm so sorry about that. Okay, so how does this work? Well, Alice wants to share a value with Bob, right? So they're going to compute a shared secret, which is going to be called S. And they're going to compute this in a way that they both know what it is, but the idea is that they can exchange information over an insecure network without anybody else being able to compute this shared value. So what do they both do? Well, they each choose a random number between 0 and p minus 1 using some pseudo-random function, pseudo-random number generator that they download off a standards website. They raise the element G that they've chosen in their group FP star. This is now looking at FP star. They raise that to the power A or B for Alice and Bob respectively. And then what do they send over the public network? They send their public key, G to the A and G to the B respectively, and then they can both compute this secret thing. And in principle, if somebody sees G to the A or G to the B, then in order to compute what A or B was, they would have to solve the discrete logarithm problem, which we suppose is hard. But this is an idea we got from the failed attempts conferences a couple of years ago. This is broken. It's not actually broken. It will be broken in a few years by quantum computers, which I'm sure you've all heard about from David Zhao and from the rest of the team working on those kinds of things in Waterloo. So we're working under the assumption today that what we want is we want cryptography that's post-quantum secure. What does that mean? That means that it shouldn't be broken by classical or quantum computers, even though quantum computers, it's still just a theoretical algorithm for the moment, because the ones we have are not very big. So what I'm talking about here is the quantum cryptoapocalypse. So why is that relevant for cryptography in a little bit more detail? So the Diffie-Hellman key exchange I just showed you, either for finite fields or for elliptic curve groups, relies on the discrete logarithm problem being hard, right? So what do I mean by hard? It means that taking discrete logarithms should be much slower than exponentiating, and it should be a sort of either polynomial to sub-exponential or polynomial to exponential gap in complexity in order to have something where you can scale up your parameters, so that for the attacker, it's much slower than for the user. And the reason we get a quantum cryptoapocalypse is because Shor's quantum algorithm solves the discrete logarithm problem in polynomial time. So that's polynomial in the logarithm of the size of the group. So with access to a quantum computer, taking discrete logarithms is about as fast as exponentiation, right? So computing g to the a is about as fast, about as slow as computing a given g to the a. So you haven't got that separation that you need to have a hard crypto system. There is a disclaimer: quantum computers that are sufficiently large and stable, right? It needs to have enough quantum bits to run the algorithm, and those quantum bits also need to not collapse for long enough to run the algorithm. So it needs to be both large and stable. They don't exist yet. I've written probably because who knows what is happening in secret, but I think we can be fairly confident that they don't exist. But they're likely to only be a few years away. I've written this. A few depends on who you speak to. There was a lovely talk last week at the Elliptic Curve Cryptography Conference that was in Taiwan, which was a panel discussion of different experts in quantum computing, quantum cryptanalysis specifically. And Sam Jake, who's a PhD student in Oxford working on the precise complexity of quantum algorithms applied to this kind of cryptography, said that his median estimate for this breaking the crypto that we're currently using would be 2043, but with a very large variance, which is going up to sort of 5 years from now. So that's at least one expert's opinion. Okay, so what can we do about it? Well, let's think about how we can think about Diffie-Hellman. So Diffie-Hellman, the idea is that we do Alice and Bob each do a thing, and whether Alice does it first and then Bob does it first, or Bob does it first and then Alice does it first, they should both arrive at the same point. So you can think about this as walking on a graph. So here's a very regular looking graph, otherwise known as Manhattan. And here we go. Alice, I think Alice was red. So Alice takes the red path and Bob takes the green path. And here's another way that they can exchange. They can each send their coordinates to each other. They can then teleport to each other's locations and then walk the same lines, the same orientation again, and end up at the same point. So this very rigid direction means that they can do their paths in either order and end up at the same point, although the paths look different. But it's not really very useful for cryptography, because anybody who knows that two endpoints of the path can compute a path between those 2 points and then imitate Alice or Bob by walking from their endpoint to where they would end if they did their path again. So the path that they walk has to be secret. Right, so the problem is it's trivial to find paths. For example, you can just subtract the coordinates and take a path that way. So what do we do about it? Well, we use isogenies. So the big picture is that isogenies are a source of exponentially sized graphs. So the idea of using isogeny graphs is something for this specific problem in cryptography was a paper in, I think, 2006. The graph I'm going to talk about in 2006. So that was Kristen Lauter and, my brain is failing me,
Charles, Gorin, and Lauter.
Thank you, David. Charles, Gorin, and Lauter. Had a little bit of a mind blank there. Charles, Gorin, and Lauter. And then David, Zhao, and Luca de Feo, and later Jerome Plut thought, hey, why don't we also use this for a Diffie-Hellman key exchange? But there was a trick which they needed to add, which we'll get to in a little bit. Okay, but the nice thing about this is isogenies are a source of exponentially sized graphs on which we can walk efficiently. So we can go between two vertices efficiently. And we have fast mixing, meaning there's short paths to almost all nodes, which is very important because in a very short number of steps, you're at an indistinguishable point in that graph. And think about what that means. That means that if you share your location, then someone's not going to be able to figure out how you walked there. Unlike the problem we had in Manhattan. And well, here's a sort of consequence of these facts. There's no known efficient algorithms to recover paths from endpoints, at least under the right circumstances. But there's still enough structure to navigate the graph meaningfully, right? So remember in the Manhattan example, the structure came from, the direction, which was the literal direction, the north, east, southwest, and the fact that you can do those directions in either order. So you need some sense of direction on any graph that you might use. And there is a sense of direction on isogeny graphs, it turns out. So it's easy, quote unquote, easy to construct graphs that satisfy almost all of them, which wouldn't be enough for crypto. But isogeny graphs, at least under some circumstances, do satisfy all of these things. So they're really useful for that. Okay, in order to explain properly what these things do, and definitely in order to explain our failures to attack and successes to construct things that we can attack, I need to go delve a little bit into the maths behind this. So if you're not a number theorist or you haven't had much exposure to number theory, this is going to be a little bit hardcore, and I do apologize. But do stop me if you need me to slow down. I'll give you a little moment at the end of each slide. Okay, so number one, we need to know about elliptic curves. So the elliptic curves are going to be the nodes of the graph. And for the purposes of this talk, we're going to think of an elliptic curve as just a polynomial equation, y squared equals x cubed plus ax plus b, right? So the variables here are x and y, and a and b are going to be fixed values that define the elliptic curve. And typically in crypto, they're going to be values in a finite field. So a point, when I say a point on E, a point on the elliptic curve, what I mean is a solution to this equation, or the point at infinity, as we call it, which we just think of as lying on every vertical line that passes through this elliptic curve. So one of the main reasons these have been studied for such a long time is that it is actually an abelian group, right? So the set of solutions to the equation plus this point of infinity is an abelian group. We can add points. So add is just a formal definition of what we call addition. The neutral element, so the identity of the group, is that point at infinity. The inverse of that element is, the inverse of a point xy is x minus y, and the sum of 2 points, the group law that we define to go between 2 points, is also easy to compute. I'm not going to go into how, but I am going to show you very quickly that there are formulas that I don't want you to remember, but they are just formulas that you can type into a computer and figure out. Oh, okay. Are there any questions about this? Okay, so the next thing we have to think about is we've got our nodes of our graph, right? We've got our endpoints. The question is, how do we pass between those nodes, right? And the answer is isogenies. So if you've got two elliptic curves, you've got two of these polynomial equations, how do you pass between them? Well, you're going to use a rational map. It's going to be, you've got not just equations, but something that's something to do with an abelian group. So that rational map, we also want it to preserve the group structure in some way. And that's essentially the whole idea behind what an isogeny is. But here's a more precise setup. So an isogeny of elliptic curves is a non-zero map from E to E prime. So E and E prime are both elliptic curves that's just given by rational functions, and is also a group homomorphism. And an extra nice thing about this is that if that isogeny is separable, if you don't know what that means, then forget it. But most of the time it's separable. The degree is just the size of the kernel, and the kernel is always finite, as it turns out for this. And so you can literally just read off the degree from the size of the kernel. So here's an example. For any non-zero integer m, we have the multiplication by m map, which just takes a point on your elliptic curve E and adds it to itself using this group law m times, right? So that's the definition of multiplication, is adding something to itself that number of times, right? So that's literally just what you would expect it to be. That's an isogeny. It has degree m squared, right? And it's a separable isogeny if m is not zero in the field over which this elliptic curve is defined. And so if you have a degree m squared separable isogeny, what do we know? Then the size of the kernel is m squared. And in fact, in this case, we know a little bit more. The kernel is isomorphic as a group to z mod mz cross z mod mz. So it's just a product of two cyclic groups. And this E square brackets m thing here, that's called the M torsion group. And that is just the kernel of this multiplication by m map. And this is notation that will come back. So I apologize for all the notation. So just try and remember what that E square brackets m is if you haven't seen it before. Any questions about this? Okay, I think the next is another example of an isogeny. Yes. So that was quite a simple isogeny that was just multiplication by an integer. So you can also have something which isn't necessarily just an integer. So for any a and b, right, so a and b were the things that we use to define our elliptic curve, the coefficients. There is a map here which I call iota because I'm going to associate it with the complex number square root of -1, which maps xy to minus x square root of -1y. And that's a degree 1 isogeny of the two elliptic curves, taking y squared is x cubed plus ax plus b to y squared equals x cubed plus ax minus b. So then they're really different elliptic curves, but it's a degree 1 isogeny, which is an isomorphism. That's the definition of an isomorphism in this case. The kernel is just the pointer to infinity, so these two curves are always isomorphic. And as a sort of fun fact, you can see that if b is 0, then this is actually just an isogeny from an elliptic curve to itself, like the multiplication by m map. And that's something we call an endomorphism, which will also come back, but will also be written down on the slide. Okay, I think I have one more example that's just a little bit more complicated to show that it's not always so easy. Yep. So here's another example of a rational map, right? So here you actually see the rational thing coming in where you've got a quotient of polynomials, but it's still just polynomials on the numerator and the denominator. And this defines a degree 3 isogeny between these two elliptic curves over the finite field F71, right? So what do I mean? That means that the coefficients of the elliptic curve are thought of as numbers modulo 71. And if you play around with these formulas, you plug them into the left-hand side, and then you simplify, then you're going to get the thing on the right-hand side. And it turns out that the kernel has these 3 points in it, and that is then just an order 3 subgroup of the full elliptic curve. And so that means that the isogeny, since it's separable, is a degree 3 isogeny, or we sometimes I might write later just 3 isogeny rather than degree 3 isogeny. I think this is my last isogeny example. So if you've got an isogeny question, now's your moment. Okay. Oh, well, okay. So now there's a very special type of isogeny, which I already mentioned in words, which is an endomorphism, right? So an endomorphism of an elliptic curve E is an isogeny that takes the elliptic curve E to itself, or it's just the zero map, which, I mean, does take E to itself, but it's not an isogeny because we said an isogeny was non-zero. But that's just a sort of silly technical thing. And the set of all the endomorphisms of E actually forms a ring called the endomorphism ring. And that's denoted by this end of E here. And this is going to be really important for our attacks. There's one more, maybe two more really nice facts about isogenies. So each isogeny, any isogeny, phi from E to E prime, always has something called a dual isogeny. And that's a uniquely defined isogeny, which I'll write phi hat, which goes in the other direction. So E prime to E. And so this is sort of approximating the inverse that you'd have with an isomorphism. But instead of getting the isogeny composed with its dual being the identity, you get the isogeny composed with its dual being this multiplication by m endomorphism that we saw as the first example of an isogeny. So in this case, the m is the degree of that isogeny itself. Ooh, okay. Sorry. Okay, hopefully everybody's happy with that so far. Now, I've also touched on this a little bit already, but just it turns out to be quite important for us. So the next maths background, the third maths background slide is fields of definition. So up until now, everything I've talked about has been over the algebraic closure. All the statements I've made have been over the algebraic closure of the base field of the elliptic curve. And for arithmetic, we need to know exactly which fields objects live in, right? So we can't just always say, oh, we'll just assume it's FP bar, because this is normally over finite fields, and you can just take the algebraic closure. But we also need to know, like, really which extension of FP we're working in. So this is terminology I've already used. An elliptic curve or a point or an isogeny or whatever we're saying, we say it's defined over K, a field K, if the coefficients of its equation or formula lie in that field. So I'll often say over something, and that's what that means. And here's another little bit of notation. For an elliptic curve E defined over a field K, we write E round brackets K to be the points of E defined over that field K. Oh, that's it, sorry. Okay, fourth maths background slide, isogenies and kernels. So remember we said that the degree of the isogeny, if it was separable, was determined by the size of its kernel, but it's actually even stronger. Isogenies are determined by their kernels. So you actually only need to understand the kernel of the isogeny to be able to reconstruct the isogeny itself, which makes them somehow quite nice and easy to handle, because if you think about the examples we've seen, the kernels are often just like points in, you know, F71 in the example we saw, whereas the map was that huge thing that looked like quotients of polynomials. So if you can just remember the kernel, that's a much easier thing. So the precise statement of what I'm saying is that for any finite subgroup G of E, so then I'm talking about the points in the algebraic closure of E, there exists a unique up to isomorphism of E prime, separable isogeny phi G mapping E to E prime with kernel G. Right? So given a subgroup, you can construct an isogeny with that kernel. And as laziness or abusive notation, or I don't know if it's really abuse, but we often just write E quotient G for E prime instead of sort of writing it all out like this, because, you know, the isogeny is just determined by the kernel. So why write it in another way? And if G is defined over K, with K the base field, then the isogeny, the coefficients of the isogeny, and the image curve, the E quotient G, are also defined over K. So then you can make sure that you stay in the field that you want to be in just by taking a kernel which is defined over that field. This is not an if and only if, this is really an if then. So Velu published some formulas in 71, which compute directly E quotient G from this kernel just by evaluating the isogeny at a point. And the complexity of computing Velu's formulas grows with the size of the kernel, so it's only suitable for small degrees. I don't think I've put this on the slides, but there's actually a very recent development in this. You would think that 1971, this is not going to change. But this year or last year, there was a paper about which we've taken to calling Velu square root or square root Velu, which actually shows that there's a trick to rearrange your equations essentially, which allows you to for the complexity of computing isogenies to grow with the square root of the size of the kernel, which is for larger degrees really quite a win. But for the small degrees that we're talking about in SIDH, it makes no difference. I mean, it's actually slower, their algorithm. So the degrees in SIDH are just going to be 2 and 3, so then it doesn't matter so much what that is. Okay, but here's a very important thing. Velu operates in the field where the points in G, the kernel, live. So we need to make sure the field extensions stay small for desired group sizes, right? Because we're thinking of our elliptic curve as having coefficients in a certain field, for example, FP or FP squared. But in principle, the points in the kernel might be then over some, extension of degree L, where the size of the kernel is L. And this is actually why we use supersingular curves, because it's easy to construct curves where the points are always going to be in small extension fields or just in FP squared. I'm not sure if I've come back to that or not, but I can later if you're interested. Oh, okay. So any questions about this? No? Okay. All right. So we're nearly there. Remember what we were trying to do is we were trying to construct a supersingular isogeny graph where we have a structured way of doing a graph walking Diffie-Hellman. And then we can exchange our endpoints and do our structured walk to get to the same shared endpoint. Okay, so we're nearly there. This is now the definition of the graph. Let P be a prime and let Q be a power of P. So we say that an elliptic curve E over FQ is supersingular if P divides Q plus 1 minus the number of points in FQ. And the cases that really come up in crypto are the quite simple versions of this. So we just care about the cases where Q is P, so that the number of points E of FP is P plus 1, and Q is P squared. The number of points in E is P plus 1 all squared. So this is what I just said on the previous slide. It's an easy way to control the group structure by choosing P. So you can choose P to be some very smooth number minus 1, so that P plus 1 is just a very smooth number. And then you've got lots of small divisors. And then you've got lots of points of very small order, which you can use for the generators of your kernels of your isogenies. Okay, so here it is. Our supersingular isogeny graph over FP squared will consist of vertices given by supersingular elliptic curves up to isomorphism, and edges given by equivalence classes of 2 and 3 isogenies, so that's degree 2 and degree 3 isogenies, both defined over FP squared. So I've written here what an equivalence class is. It's not really that important for the intuition, but in case anybody's stressed about it, then it's there. Okay. There's no questions about this. I think I have a picture. Yeah, here we go. So the isogeny graph looks like this. Here's a picture, a toy example of an isogeny graph. So now here the base field FP is 431. So P is 431, but the base field is FP squared. So this is, each black dot represents the an isomorphism class of supersingular elliptic curves defined over fp squared. And the orange lines represent two isogenies between elliptic curves, and the blue lines represent three isogenies between elliptic curves. So this is the graph that we're walking on, because we're taking, so Alice is going to walk an orange path and Bob's going to walk a blue path, and they're going to share their endpoints, and then they're somehow going to walk kind of the same path, the same directions. The somehow is yet to be determined why. Okay, so the somehow idea is really the key idea behind SIDH, which was published by Luca De Feo, David Zhao, and Jerome Plut in 2011. In order to give an idea of exactly how this works, I want to just return to the example right from the beginning of the talk, Diffie-Hellman, and I'm going to write it in this slightly strange way. So Diffie-Hellman you can really think of on a high level as just being this sort of commutative diagram where Alice computes the horizontal arrows and Bob computes the vertical arrows. And then they end up, they do that in the different orders, and they end up both at this bottom right-hand corner with G to the AB as their shared secret. And this is kind of the same high-level view for the SIDH Diffie-Hellman key exchange, but our elements just got a bit more complicated. So here's the high-level view. Alice, again, computes the horizontal arrows, and Bob computes the vertical arrows. But now what do we have? Alice's secrets are in red. So Alice knows a secret subgroup A of the elliptic curve E, and she computes the isogeny with that kernel. And Bob knows a secret subgroup B of the elliptic curve B, and he computes the isogeny with that kernel. And then just like in classical Diffie-Hellman, they're going to share their respective public elliptic curves where they get to, and then they're going to do something else. Okay, so here's what I've just said. Alice and Bob pick secret subgroups A and B of E. Alice computes the isogeny with kernel A, and Bob computes the isogeny with kernel B. Alice and Bob transmit the values E quotient A and E quotient B, respectively. And then Alice somehow obtains A prime, which is the image under Bob's isogeny of her secret kernel, right? And Bob's going to find B prime, which is the image under Alice's isogeny of his secret kernel. And then using that, they can both compute the shared secret because of some elliptic curve magic. Turns out that the quotient of E quotient B with A prime is isomorphic to the quotient of E quotient A with B prime. And for that reason, we sort of write it just as the E quotient A and B. Sorry. Any questions about this? The somehow will obviously be explained. Okay. So where does this somehow is on the next slide? Alice somehow obtains A prime is phi B of A. But of course, Alice only knows A and Bob only knows phi B. So the solution to this problem, which is the key idea that was in this paper, SIDH paper, is that phi B is actually a group homomorphism. So if you know the generators P and Q of the A torsion of the elliptic curve, and you know the image of those generators under phi B, then you can also compute the image of the kernel without actually knowing exactly what that A is. That A can be anywhere in that box. And if you know the image of P and Q, then you can compute phi B of A for anywhere in that box, just by using its property that it's a group homomorphism. Okay, so just to write that in a more precise way, Alice picks her secret A by taking generators, public generators, P and A of the A torsion, for fixed public P, Q, and E. And then Bob includes the images of those public points under his isogeny in his public key. And then Alice can compute A prime, right, the image of her secret point under Bob's isogeny, just by splitting it up into group homomorphism and taking phi b of p plus a phi b of q. And then it's the kernel generated by that. Any questions about this? No, okay. So here's a little summary. Hopefully it won't seem too much now that we've seen all the parts of SIDH in one slide, just how it works. So again, we've got public setup parameters. So we're going to take a large prime P, which is going to be 2 to the n times 3 to the m minus 1, and a supersingular elliptic curve E defined over Fp. Public bases PA, QA, and PB, QB of the 2 to the n torsion of E and the 3 to the m torsion of E, respectively. Now, what does Alice do? Alice takes a random number between 0 and 2 to the n minus 1, and then she uses that random number to generate a random 2 to the n torsion point A, the generated kernel generated by a random 2 to the n torsion point. And then she computes the isogeny with that kernel, right? So that's going to be an isogeny with the cyclic kernel. And Bob does the same thing, but with B. And then they share some public information. So it's not only the endpoint of the walk, actually, which is the E equation A, but it's also the images under this secret isogeny phi A of the public points corresponding to B, and likewise for Bob. And then they can use that to compute the second kernel they need to do the second steps in the commutative diagram, and get the shared secret, which is just the quotient of the elliptic curve by the two subsequent kernels. And then that J is just an isomorphism invariant, because remember, they were only the same up to isomorphism. So this is kind of the high level overview of how it works. And so when this was first published, people were like, this is really cool. But okay, I don't know about when it was first published, because I wasn't really thinking about these things then. But at least a few years later, people were like, this is really cool, and I don't have any ideas to attack it. But I think it might not be safe because of the public images of the points. But nobody came up, well, there was a couple of ideas, but no ideas that were actually going to give a passive attack on the scheme. And I think mostly it looks nice and simple like Diffie-Hellman, so people want it to be exactly like Diffie-Hellman, but it's much less messy than some other post-quantum key exchange schemes where you're sharing so much information, like way more than this. So I don't really know why people make that argument. I hope you're not one of those people, otherwise maybe you hate me now, but that's the way I feel about it. Okay, so you attack this scheme by, if you're an attacker, what do you want to do? Given the public information, right? So given the two elliptic curves and these images of the points, you want to find the secret key, which is the isogeny phi A or phi B respectively, or just the kernel, because remember, from the kernel, we can compute the isogeny itself. Any questions about SIDH before I move on to how we try to attack it? No? Okay. Okay. So when I say breaking SIDH, I don't necessarily mean actually breaking the scheme. I just mean like solving the isogeny problem, which I will almost always not mean breaking it actually. So given supersingular public elliptic curves E0 and EA over Fp squared, connected by a secret 2 to the n degree isogeny phi A, and the action of phi A on the 3 to the m torsion of E0, so that's just the image of these public points, so you can deduce the action on the 3 to the m torsion from that. Find the secret key. This is weird English, I'm sorry. So you recover the secret isogeny phi A. So that's what I mean when I say breaking SIDH. Now I'm going to just mention a couple of papers which talk about how to use these image points to do that, given stuff we don't necessarily have. So in 2016, Galbraith, Petit, Shani, and T, they showed that if you know the endomorphism rings, so remember that's the set of all the maps from the elliptic curve to itself, of both E0 and EA, then there's an efficient algorithm to break it, so to recover this phi A in some feasible amount of time. And in 2017, Christophe Petit showed that, in fact, with E0, this special curve y squared is x cubed plus x, which is the curve that's used in SIDH, or at least it's always close to the starting curve that's used in SIDH. And these very specific parameters, 3 to the m is greater than 2 to the 4, n is greater than p to the 4. So the way that you think about this is that Alice's isogeny is much, much, much shorter than Bob's, and they're both way, way longer than they need to be. So this is not very realistic assumptions, but this is the assumptions you need to use his methods to construct a non-scalar endomorphism and then use this attack of Galbraith, Petit, Shani, and T to efficiently break the scheme. And so, yeah, in SIDH, of course, we don't have these weird parameters. You've got something which makes more sense computationally, which is that Alice's and Bob's isogeny are about the same length, and they're just the right length they need to be in order to get the security that you expect. So 3 to the m is about 2 to the n is about the square root of p. So it's nowhere near this balance. So Christoph's method is actually like quite a lot more general. So I've said 2 to the n and 3 to the m here, but it doesn't really matter. It just needs to be kind of smooth. So I'm just going to replace the 2 to the n by a d for degree and a 3 to the m by a t for torsion. And then otherwise everything's the same. Okay, so how does this work? Well, you need to get from these public torsion points to an endomorphism, right? So the endomorphism, the things that allow you to apply this attack. So here's, I'm really talking about the case that Christophe did in 2017, which is starting from this E0, which is used in psych, for example, or a neighbor if that one is used in psych, and with these very strange parameters. So what do you need? You need to find a secret. The secret's all in red. The secret isogeny phi A or its dual. If you find the dual, you can actually find the isogeny itself of degree given degree d. So E0, because it's this special curve, you can actually choose any endomorphism. We know the endomorphism ring of that. So you can choose any endomorphism you like. So because we know it, I've put it in green. So you can choose every endomorphism in the world on E0. And then what you can do is you can sort of trace your map around from E, and you can create an endomorphism on E. So remember, an endomorphism is a map from E to itself. So you literally just sort of trace the diagram. You take phi A dual, then iota, then phi A, and you end back at E. And then you get an endomorphism that I've called theta on E that you also don't know because you're composing with maps that you don't know. And you can also add some multiplication by n to that because that's something you can always compute on an elliptic curve that you know. All right, what do we know? We know the action of phi A and phi A dual on the T torsion. We also know the degree of theta because we know the degrees of all of the maps it's composed of. Then, if there exists a iota and an n such that degree of theta is t, you can completely determine theta because you can just use the knowledge on the T torsion to figure out what theta is. And then from that, you can deduce the secret isogeny phi A. And what you can do is you can also add a small number in front of that T to make this a bit more of a feasible problem. Let's call it an epsilon because epsilon is meant to be small. And then you can sort of finish it off with a little bit of brute force, which happens to take square root complexity. So then what you can do is you can completely determine theta and phi A in time, which is going to be mostly dominated by the square root of epsilon, because epsilon we're assuming is we can make that a little bit bigger than polylog and still have interesting problems. And so what Christophe showed in 2017 is that you can heuristically do this for polynomially small epsilon. even though I just said we're going to talk about it bigger, but that's in a minute, when t is greater than d to the 4 is greater than p to the 4. And that's where this parameter imbalance comes from. And it's actually I don't know why Christoph didn't do this in his original paper. You can also just think of, you can put a square on that t just by instead thinking of saying, well, if theta has degree epsilon t squared, then you can decompose it into two isogenies of degree t and one of degree epsilon, which is then in the middle. And you know the action on the t torsion, both of the dual of this one and the non-dual of this one. And then you can reconstruct it just using exactly the same methods. And that gives you a better balance already. And there was actually quite a fun thing, which was while we were thinking about these things, a team of people, I think some of them are in Waterloo, so I've written down their names in case they're here. Bottinelli, De Quayan, Leonardi, Mosunov, Polega, and Chef. They came up with a really new idea to get this, to do this, which uses some other crazy things which Christoph didn't have in his original paper, which is also really fun. But it's kind of sad that it turns out to be the same balance and not a better balance. But it was a better balance than the one that was public at the time. And we've talked to Victoria De Quayan, who I think a lot of you know, about trying to combine these ideas, but I think she's fairly convinced it's not possible. So I don't think we can combine them to get further, which is a little bit sad. But that's life. But anyway, so this is just this is not the main point of our paper, but it's just pointing out that this square means that the balance is better than it was. Okay, so why does this work? Well, we know that the degree of theta is d squared times the degree of iota plus n squared. And so this is just the same thing again. We know that epsilon t squared is the degree of theta, which is d squared degree of iota plus n squared. And how do we do that? Well, we take iota in end E0, and then because of what we know about E0, we can basically assume that the degree of iota is PA squared plus PB squared plus C squared, where P is the E0 is defined over FP, and A, B, C are all integers. The algorithm's in two parts. So this is a pre-computation, which is finding A, B, C, and N and epsilon in Z with epsilon small as possible, such that this equation is satisfied, which is just the two parts. It's d squared times the degree of iota plus n squared is epsilon t squared. And then reconstructing, this is then the online cost, is reconstructing a iota with that degree and using that to compute the isogeny itself. Oops. So solving this equation is actually something with epsilon small enough, is something that we don't know how to do. And so this is something I like to point out in every talk, just in case somebody has a super idea that we haven't thought of yet. So here's a little picture of our attacks. So on the left-hand side, that's our actual results. So here, the bottom axis, the alpha axis, that's talking about the size of Alice's isogeny, and the beta axis is talking about the size of Bob's isogeny. And so everything that's above the red, in the red section of the graph, that's a polynomial time attack. Everything in the orange section of the graph is a classical attack that improves on the previous best classical attack. And everything in the yellow section is everything that improves on the previous best quantum attack. And so we're just looking at the balance between the parameters here, and we're trying to get that as good as possible. And on the left, so yeah, that's our results, and the dotted lines are under the one-to-one dotted line is everything that would apply to an SIDH group key exchange, which I think was done by a few people in the audience. And everything below the 2-to-2 dotted line is parameters that you have in a fairly new suggestion called B side. And essentially, we feel like these lines shouldn't have an an angle in them, and it must be possible to get the picture on the right. And it would be possible to get the picture on the right if the pre-computation cost was better. So the sticking point here is the pre-computation cost of the algorithm. So the right-hand picture, obviously you see this green dot is SIDH, which we're never going to break no matter how hard we try. The picture on the right is would be the cost of the attack, the online cost of the attack, if you could solve the equation with solutions of the required size in polytime, or at least time less than the online cost. So on the next page, here is what we've come to call the equation of death. So this is the equation that you need to solve. And this is the as precise as I could get it. For square root p is about d is about t and p large. You want to find a, b, c, n, and epsilon in z, with epsilon about the square root of d cubed times p over t, such that this equation holds. So d squared times pa squared plus pb squared plus c squared plus n squared is epsilon t squared. And if you can solve that in polynomial time, then you can get this right-hand picture. And I think this is a fundamentally hard question, although maybe somebody will say, hey, actually I have an idea, which is awesome. But if it is indeed a fundamentally hard question, then we can't get over that barrier to break group key exchange. So, well, David's serendipity continues, I guess. Okay, and so I wanted to say just a couple more things quickly about what's in the paper, because it's not just about this very specific setup. We started looking at things that we were better at solving, we were better at breaking, just to make ourselves feel better, essentially. So this is the situation that we had. Just here's a little recap. The case is E0 is this special curve, y squared equals x cubed plus x. And you need to find the secret isogeny phi a, and our algorithm does that in time, square root epsilon times polylog p. When t is bigger than d squared is bigger than p squared, that's polynomially small e, but for when we've got these balance parameters like in SIDH, that gives you this sticking point, this bound on epsilon that just comes from the norm equation of the endomorphism ring of that elliptic curve. So the natural question is, can't we just change the starting elliptic curve to something we can break? And the answer is yes. So if you specially construct your E0 to be broken on purpose, then you can change this condition to t is greater than d squared. And the big difference here is that you don't have a condition on p. And this actually makes it just much more viable and a much more interesting thing. And that would apply to, for example, group key exchange with 3 or more parties. And then this is a break when I say a break is in time p to the 1/8, which is a square root speed up compared to the best known attack. So it's definitely not a break. It just means that the parameters would have to be bigger. But it's really, really not a break, because it's a specially constructed E0, which is not the starting curve that we use. But at least we've constructed something that you can break. So there you go. Don't use the thing we constructed. So this is a square root improvement over the previous best known attack, as I said. So just a final little summary, SIDH is still not broken and probably never will be. Don't quote me on that. So allowing for attack complexities up to state of the art, the balance of SIDH is exactly at the point where torsion point attacks give no improvement. So that's what I was showing you on the two left-right pictures. This last slide that I just did was saying that there are many I didn't say there were many. There are many, it turns out, specially constructed starting curves allowing for an attack, but probably none of those help with attacking SIDH proper. There's a little bit of work to do to prove that that's true, but based on some conversations we had at a research workshop after ants, I'm fairly sure that that is true. One more thing I haven't had time to talk about, which is that you can also construct special base field primes. So that's where the coefficients of the elliptic curve live, to get efficient torsion point attacks, which of course also don't apply to SIDH proper, but it's also kind of a fun thing you can do to construct broken things. So I think that's pretty much all I had to say, and I'd be happy to have any questions.
Well, thank you very much, Chloe, for the nice talk.
Thanks.
So let's see, anyone have questions for Chloe?
I have a question.
Yeah, I'm just going to stop sharing my screen so I can see you all. Hi.
Thanks for the talk.
Thanks.
So you say you can construct special either E0s or primes that would make it broken.
Yeah.
Is it possible to do that sneakily? Like if you were to give me a standard with a broken thing in it, could I tell you had done that?
So that's a very good question. And it's something that we did think about, but we couldn't really come up with a satisfactory answer. That might be because we're not good at formal statements or something. But so essentially, if it was broken enough for you to be able to use it as a backdoor, then it would be detectable, because essentially you figure that out by constructing by breaking the scheme. So you can always just try and see if you get it, and if it wasn't broken enough, if it was just like, I don't know, square root speed up, like the example I gave on the best known attack, then that's not something that you can really just try and see if it works, because you're still then talking about a huge, 64-bit at least.
But there's not a way to embed a secret in the bad parameter such that only if you knew the secret could you get the speed up.
There might be. It's not impossible that there is, but we haven't explored that enough for me to give you a definite answer of yes or no. But it's definitely an interesting thing to think about. We've put some vague statement in our paper, like maybe you can do backdoory stuff with this. Maybe, I don't know. But I think it's something that should be easy to prove. Not easy. It should be possible to prove that you can't, or prove that you can, of course. But my instinct is that if it's efficient enough to be a backdoor, then probably you can't detect it. Sorry, then probably you can detect it just by trying to break it. Yeah.
Thanks.
Okay, other questions?
I have a question. You say that you say that you chose iota to have trace 0 for simplicity. Do you get any like mileage out of using iota that don't have trace 0?
Also a good question. No, we have thought about that a lot, and I don't think you can. You kind of end up with the same problems, but in a more complicated formula. Essentially, I mean, you end up with the same bound restrictions as far as we can tell. At least with E0, we haven't really. We may not have explored that sufficiently on arbitrary curves, but I think on E0, you can't get enough from saying trace non-zero.
Yeah, I mean, I haven't thought about it.
Well, you don't want to break your own thing. That would be embarrassing, no?
Well, but it seems that if you use a more general iota, then the equation would get more complicated. Of course, it might be easier to solve. I don't know. Sometimes a more complicated equation with more variables gives you more freedom.
I also hoped it would be easier to solve, but well, at least I couldn't solve it. I mean, I couldn't. I got the same sort of bound restrictions with non-zero trace. But I mean, these questions are definitely non-trivial, so I'm not saying that that's impossible. But I think there's there's also more general there's more general theorems about sort of the sizes of the norms of these things that will make it not work for E0. Just thinking about Jonathan Love and Dan Bodney's paper this year, looking at the troughs and the valleys of endomorphisms of different norms will give you this. I think that gives you a sort of a real proper reason why this doesn't work, or at least why you get the same bounds.
Hi, Angie. All right, thanks.
Yeah.
I told you I was picking up my kids from school. So there you go.
Yeah. It's dedication to bring the talk to the kids' school.
I have a question.
Yeah.
Well, great talk. Thanks. So, is there any chance of going from like polylog to log?
Oof. Maybe. It's not something we thought about. I think the answer is probably yes, but you'd have to do a lot more analysis to figure out exactly where the polynomial powers come in, and probably the balance would get worse.
Mm-hmm.
But yeah, we were sort of trying to do the opposite. We were trying to allow for sub-exponential and exponential complexities and make the balance as good as possible. But I think you can sort of go the other way as well. If you want to go to log, you could make the balance worse. And
Right, because like so there's kind of like an interesting like I wouldn't even say analogy, almost like a mapping to if you instead of working at the finite prime p, if you work at the infinite prime, and you end up working with like arithmetic subgroups of SU2, which show up in quantum computing. And so there, like, we've developed algorithms that essentially like factor the non-commutative ideals, or the ideals in these non-commutative rings. And you can essentially like achieve like, like log 1 over epsilon, like length approximations. And something that we only realized after the fact was that Kristen Lauder's algorithm, which was an attack, was actually like, could actually be, we almost like rediscovered the algorithm. And I feel like this is something that nobody's really quite worked out yet, but like folklore, I've been told they're the same thing.
Okay.
So just, I don't know, it's just an observation, but like, but we did kind of have a very general way of working with essentially like arbitrary S arithmetic subgroups, not just at 1 prime. So it looks very similar, like it's kind of reminding me in your talk, there's a lot of similarities with this kind of dual collision picture.
Yeah, so
like people had tried.
I mean, I think I have to read. Is it a paper?
Yeah, there's a couple papers like Yard Klichnikov. They're on the archive. But I think you might be better served to look at some of the stuff that has come out of Peter Sarnak's group lately, like his papers on like arithmetic golden gates.
Ah, okay. We have actually had a little look at that.
Because like these supersingular elliptic curves, right? Like their endomorphism algebras are,
yeah, the endomorphism algebras are a quaternion algebra ramified at p and infinity,
right?
And the idea
like lift them to number fields or something to make it work, or something like that.
So I do wonder if I have to read your paper to be sure how to answer your question as precisely as possible, but there is a recent paper by Christophe Petit as well, and Peter Kutas, two of my co-authors, and Charlotte Weitenkamper and someone else. I have to look it up. Where they do map the quaternion ideal problem, so that could have something to do with your non-commutative subgroups into a number field setting, and show how to sort of get the Torsion-point attacks on a commutative subring, which means that they can then use a sub-exponential quantum algorithm on that, but it doesn't give a speed up because you've still got some other stuff going on that makes it not work. But it is an interesting idea, and I wonder if it's related in some way. I have to think about that. That's a good one. Because if you can factor your ideal into smooth ideals, your quaternion ideal, then you can maybe reconstruct that.
I don't know if anybody's written down the relation between these, but it's something that like we've like, to be honest, I worked in like the building next to Kristen, and we even told her like when we discovered this stuff at Microsoft, and it was only like 2 years later that we realized it was really the same thing. Like we convinced ourselves at the moment, oh, they're totally different, like because they're completely opposite applications. But I sort of feel like nobody's really analyzed this yet. I don't know.
I think we should definitely talk about this.
I don't know.
Yeah, no, it's definitely worth exploring.
Yeah.
But yeah, let's talk about it more offline, maybe.
Yeah, for sure.
I think it's a good time to thanks, Chloe, and we can have people discuss a little bit after the talk. So thank Chloe for the nice talk. So now it's the visual